this module, you will learn about the measurement of length or distances. You can easily measure length of various entities using appropriate instruments such as a tailor's tape for length of a cloth, a land tape for length of a building, a survey chain for length of roads, etc. However, lengths to be measured can be as large as distance between two heavenly bodies or as small as the radius of an atom. To measure large distances, we employ an important method called the parallax method. What happens if you look at an object with one eye closed? Its position seems to be moved a little from the original position. If you look at a pencil held in front of your eyes against a fixed reference point on a plain wall, with your left eye closing your right eye, and then with your right eye closing your left eye, you observe that the position of the pencil seems to change with respect to the fixed reference point on the wall. This is called parallax. You may call the two eyes are two different viewpoints, since when used separately, they create different lines of sights. Distance between these two viewpoints or points of observation is called basis. Here, the basis is equal to the distance between two eyes. We use exactly the same method to measure the distance of a distant planet. Instead of two eyes, we view the planet from two different observatories on the Earth at the same time. Let X and Y be two observatories viewing the planet S from two locations on the Earth. Thus, XS and YS are the lines of sight of the planet from the two observatories respectively. Here, the distance B between X and Y is the basis which is known. Thus, XYS forms a triangle. Let beta and gamma be the angles made by the lines XS and YS with the line XY respectively, and angle XSY be theta. The angles beta and gamma are measured while observing the planet with the help of telescopes. As the sum of the angles in a triangle is equal to 180 degrees, and knowing the values of beta and gamma, we calculate the angle XSY between the two directions along which the planet is viewed from these 2 points. This angle, denoted by theta, is known as parallax angle or parallactic angle. As the planet is at very large distance from the Earth, say D, its distance from the two observation points on the Earth, namely XS and YS, can be approximated to be equal. As D is large, the ratio of B to D is less than 1. This implies that the parallax angle theta is very small. Subsequently, we consider X and Y as 2 points on arc of a large circle with its center at S and radius D. By definition of angle, theta is equal to the ratio of the arc length, which is the basis B to the radius of the circle D, where theta is taken in radians. Thus, basis B is equal to d theta. This implies that the distance of the planet D from the Earth is the ratio of B to theta. As we measure the distance of a faraway planet from the Earth, we can also measure the size or angular diameter d of the planet. If d is the diameter of the planet and alpha is the angle subtended by the planet's diameter at the Earth, we have alpha equal to d by d, or d is equal to d alpha, where alpha is in radians. The angle alpha can be measured from a single location on the Earth. It is the angle between the two directions when two diametrically opposite points of the planet are viewed through the telescope from the observation location. For the purpose of these measurements, you must know the conversion of degrees into radians. 1 degree or 60 minutes is equal to 1.75 into 10 power minus 2 radians. 1 minute or 60 seconds is equal to 2.91 into 10 power minus 4 radians. 1 second is equal to 4.85 into 10 power minus 6 radians. That was about large distances. Let us now look at the other side of the coin. That is, smaller distances. To measure very small distances, such as the size of a molecule, we cannot employ devices like a vernier calipers or a screw gauge. Special microscopes need to be used. However, all such instruments have certain limitations in measuring lengths. We can use a simpler method to estimate the size of a molecule. Let us take some oleic acid. Oleic acid is a soapy liquid with large molecular size of the order of 10 power minus 9 meter. To start with, we prepare a 20 cc of alcohol oleic acid solution with 1 cc of oleic acid in it, and dissolve 1 cc of this solution in alcohol to dilute it to 20 cc. This makes the concentration of oleic acid as 400th part of the solution. Next, we take water in a large trough and sprinkle some lycopodium powder on its surface. Lycopodium powder is a yellow tan powder that spreads uniformly throughout the surface of water, forming a thin layer. Then, put 1 drop of alcohol oleic acid solution in this trough. The oleic acid drop spreads into a thin, large and roughly circular film of molecular thickness on water surface. By pushing away the lycopodium powder from the point where the drop is dropped on the surface, this makes the circular film of the acid drop identifiable on the water surface. Quickly, we measure the diameter of this circular film to determine its area, A. Let the approximate volume of a drop of solution dropped on the surface of water in the trough be V centimeter cube. As the concentration of oleic acid is 1/400 in the solution, the volume of oleic acid in each drop of the solution is V/400 centimeter cube. Since only 1 drop of solution is put in the water, the volume of oleic acid on the thin film is equal to the volume of the drop, that is, V/400 centimeter cube. Now that we have the area and volume of the thin circular film, we can get its thickness, T, as the ratio of volume to area. T is equal to V/400 A centimeter. If we assume that the film is monomolecular, as the concentration is very low, the thickness of film becomes the size of a molecule of oleic acid. We learnt how to measure a tiny molecular distance or a massive stellar distance. There are various scales of measurement in this range. A brief chart of the measurable distances is shown here. Some of these units are named for usability purpose, such as Fermi, denoted by small letter f, which is equal to 10 to the power minus 15 meter. Angstrom, denoted by accented A, equal to 10 to power minus 10 meter. Astronomical unit, denoted by AU, that measures average distance of the Sun from the Earth, which is equal to 1.496 into 10 to the power 11 meter. Light year, denoted by small letter ly, which is equal to 9.46 into 10 to the power 15 meter. A light year is the distance that light travels with velocity of 3 into 10 to the power 8 meter per second in 1 year. Parsec, denoted by small letters PC, which is equal to 3.08 into 10 to the power 16 meter. This brings you to the end of this module. In this module, you learned that to measure large distances, we employ an important method called the parallax method. Distance between two viewpoints or points of observation is called basis. The distance of the star from the Earth d can be calculated as the ratio of the basis b to the parallax angle theta. If d is the diameter of the star and alpha is the angle subtended by the star's diameter at the Earth, we have alpha equal to d by d, or d is equal to d alpha, where alpha is in radians. For the purpose of measurements, degrees can be converted into radians. 1 degree or 60 minutes is equal to 1.75 into 10 power minus 2 radians. 1 minute or 60 seconds is equal to 2.91 into 10 power minus 4 radians. 1 second is equal to 4.85 into 10 power minus 6 radians.